Hi, welcome back. In this lecture, I would like to provide an introduction to Shor's factoring algorithm. That is one of the most famous, most important quantum algorithm. So quantum computing was mostly considered to be of academic rather than practical interest, something interesting but no real application. And this until Peter Shor's 1994 discovery that a sufficiently powerful quantum computer can find prime factors of a number exponentially faster than any conventional traditional computer. In this lecture, we're going to look at the basic principle of Shor principle, look at more practical aspects of the algorithm. So why Shor algorithm is important and why factorization into prime number is important? Well, it is important because the ability of quickly and in a fast way factorize very large number can help breaking the Rivers-Shamir-Edelman or RSA public key crypto system that are the base of all the crypto system used today, for instance also on the internet. Public key crypto system like RSA work by a process wherein a freely available public key can be used by anybody to encrypt information. But once is encrypted, the information can only be decrypted using a secret, privately held key. It turns out that the task of finding the prime factors of a large number n works well as part of a public key crypto system. In fact, the assurance that someone can only use the public key to encrypt and not decrypt information rests on the assumption that finding the prime factors of n is a computationally infeasible task. So this can work only given an infinite amount of time. However, if the Shor algorithms provide a way to find prime factors of a large number n, then he has a very strong implication for one of the modern internet backbone component, that is the RSA. The Shor algorithm is probably the best known example of a class of algorithms solving instances of the so-called hidden subgroup problem. What is actually that? In the hidden subgroup problem, we want to determine the periodicity of a given periodic function, where the periodicity can be potentially quite complicated and can take a lot of time to calculate. A number of problems in discrete mathematics are actually instances of the hidden subgroup problem, such as periodic finding that we will tackle with quantum computing, order finding discrete logarithms, and many others. So the most important concepts when we think about the Shor algorithm is to think that instead of attacking directly the problem of factorizing a large number n in the prime factor, we actually solve an equivalent problem. So we can state without actually a proof results from the number theory on which the Shor algorithm is based. And what is this assert? Well, it's possible to solve the problem of finding prime factors p and q. So this will be the output that you want to achieve with the Shor algorithm to determine p and q, to factorize our number n, so n equal to pq. If we are able to solve the problem of finding the repeat period of the function ax mod n, as the integer variable is varied. So we vary x, so 1, 2, 3, 4, 5, 6. We calculate what is this function, ax mod n, and then we find the periodicity, or the so-called repeat period of this function here. Once we find the repeat period, we can then calculate the factors p and q, which are prime numbers. A little bit of terminology. So n is the number that we want to factor, and a is a number that we select that we call the coprime. The value of coprime can be chosen to be any prime number that we like. So what is the repeat period of the a to x mod n? Well, this is something very similar to the period of a function. In this case, is a discrete function. To find the repeat period of a to the x mod n means that as we change the values of x, so we increase the number of x, eventually the sequence of numbers returned by this function repeat itself. So here we have the example of, we have two examples. So one using 2 as a coprime, and then using n equal to 15. And the second example on the right side, we still use 2 as a coprime, and then we use n, that the integer, the number we want to factorize, as 35. You see here we have a depiction of this function here, a to the x mod n, and you see that the function itself is repeating both here in the case of 15 and both here in the case of 35. So the period of finding in this particular case is going to be 4, because after 4 instances it keeps repeat, and this case is 12. So once we find the period, the repeat period, we are not done yet. We got the number, and we need to calculate what are the prime number p and q. So once we know the repeated period, then we can use the great common denominator, and we have here of the number n and the number that is calculating as follows. So the coprime repeat period divided by 2 plus 1. So this will give our two numbers that factorize our prime number. As I said, the GCD is a function that returns the greatest common divisor. We can use the so-called Euclidean algorithm that is going to work on the CPU. And here on the right, we have a code for calculating the Euclidean algorithm for the GCD. So it's important part that while we are going to use quantum computers for calculating the repeat period, we are going to use the GCD to calculate what are the factorization of prime number from the repeat period. We are going to calculate on a classical computer. In the next lecture, I'm going to explain how to use quantum computer for calculating the repeat period. I just want to mention now how to calculate the repeat period but using classical computer. And that also will allow us to understand how computationally intensive and what is the cost of the computation on the classical case. So what we simply do, we can calculate, so we have our number n, that's the input. We choose a prime number called coprime, that is a, and then we keep increasing x. So for increasing values of x, we count how many values we have tried and keep track of the returning values we get. As soon as one of these return values repeats, we can stop and declare the period of that number values that we try. We assume that if we get the same values back from the function, then we must have gone through one full repeat period p. A mathematical property of a to the x mod n is that it can only assume any given values once within one period. Hence, the moment we get the same result twice, we know that we have completed a full period. But this is actually easier to see with looking at the code. And this is the code for calculating repeat period in a classical case. So we have our number n, we provide number coprime and the precision bit. As you can see here, we calculate the first what is the maximum number of iteration, max loops, and this is going to be a power of 2 to the precision bits. And then we have a loop where we check if we have we check if the sequence is actually repeating. This is called repeating period. So the most important part is to look at the counting of this loop. And you see here iteration goes to max to the loop, that is 2 to the precision loop. And the output of our iteration is the number iteration, and this will be the repeat period. What is the cost of this? Well, the code shown here runs quickly on a wide range numbers. However, the complexity is biting back. So we saw that there is a power of 2. So the period finding loops only needs to run until it finds its first repetition. However, this grows exponentially with the number of bits in n. So if we do a plot, so the number of bits in n, and then we calculated the maximum repeat period iteration for finding the repeat period, we see that increase exponentially, right? So while the cost is acceptable for a small number n, is going to increase exponentially with the number of bits in n. So the complexity of the classical case, where we calculated the repeated period in classical case, is exponentially increasing with the size of n. And this is the last slides of this lecture. In the next lecture, we're going to look at the Shor algorithms in detail and focus on the quantum implementation. Talk to you soon.